Okay, we're looking at example 2 here of the disk method. We've done example 1 of kind of a simple nature, and now we'll move to something a little more difficult. So example 1 looked like this as a picture and this as a solution, and now we'll move to example 2 again on your worksheet here. So you need not write this down, but let's look at the work to figure out the volume of this challenge. We've got two functions this time, the first of which is f of x equals 2 minus x squared. The second of which is g of x equals 1. It's going to help you think about both of those if you think of them as y equals. So y equals 2 minus x squared is a parabola. It opens downward and travels through the order pair 0, 2. Y equals 1 is a horizontal line going through the y-axis at 1. So we're going to look at that graph in a moment, but the challenge here is to rotate the enclosed region around the horizontal line y equals 1. In doing so, we're going to find the volume of this shape. Let's take a look. So I've gone just 2 units in each direction here. Here is the upside down parabola traveling through the order pair 0, 2. Remember, the second curve or line, y equals 1, is a horizontal line traveling through the y-axis at y equals 1. And you can see the captured, enclosed, in-prison region here. And we're asked to rotate this around the line y equals 1. So you can picture this dotted region slowly rotating around y equals 1, picking up speed, going faster and faster until it's a blur, and you can see the three-dimensional region that results. That three-dimensional region kinda looks like this. Okay, so I know it's going to rotate around y equals 1, so if it is 1 unit above the line y equals 1, after rotation it is 1 unit below y equals 1. That's why that white line is going through the origin. And again, I am going to stack, actually not stack, but bookshelf these circles from left to right. An infinite number of circles, each of which has area pi r squared, from left to right. The limits of integration we will figure out in just a moment. In doing so, if I sum up all these areas, an infinite number of areas, that will provide for me a volume. So let's see if we can figure a few things out. You know, that little thickness associated with each circle, semi-important to think about. Infinitesimally thin circle has a thickness of dx, a small difference in x's. So I always like to provide that on my picture to remind myself, hey, this integrand is going to be entirely in terms of x. Here are your ordered pairs. Those two curves intersect at -1, 1 and 1, 1. If you've drawn a neat graph, those intersection points are apparent. If not, you simply have to take your two equations, set them equal to one another, and solve for x. And that's not too taxing if you can rewind the film to your Algebra 1 days. So I've got the first intersection point on the left is the order pair -1, 1. The second on the right is the order pair 1, 1. And remember, since we are writing this integral in terms of dx, my entire integrand has got to be in terms of x. Moreover, my limits of integration have to be x values. So hopefully you can see here, there's the radius r of the one circle that I have pictured. And we are going to bookshelf these circles from -1 to 1. If I can go back a page here, you see clearly the x values of -1 and 1 that we're going to circle, that we're going to integrate toward. All right, so that's where I steal that negative 1 to 1. Okay, so now we're going to bookshelf your disks from negative 1 to 1. That is the limits of integration from negative 1 to 1 of some area formula, which is going to be written in terms of x, and then the integrals in terms of dx. How about the area? Well, just like in the last problem, since we are summing up a bunch of circles, the area formula I'm utilizing is pi r squared. So from negative 1 to 1, we have a bunch of circles all the way bookshelf, starting at negative 1, ending at positive 1. There's an infinite number of such circles. And each circle's area can be found using the area formula pi r squared. But what is r? So I've got to think about r being equal to 2 minus x squared minus 1. Now we can look at this further so your understanding is a bit clearer. But if you take a look at that very top purple curve, the very top of the mountain there, what you're going to do, that curve is the function 2 minus x squared. Now, to find the radius of the circle, I need to subtract the lower curve. We've been down this road. If I want to find a distance between two curves, I got to go top curve minus bottom curve. The top curve is 2 minus x squared, while the bottom curve here is 1. So again, that blue radius you're looking at can be found by going 2 minus x squared minus 1. Let's see if that is going to work with our math here. So we're back to this point. Oh, back the truck up here a moment. Here's what we were looking at. The top curve, the purple curve, 2 minus x squared. The horizontal curve is 1. Top curve minus bottom curve yields 2 minus x squared minus 1. All we're doing now is simplifying that version. It looks like I'm going to have negative x squared plus 1, since 2 minus 1 is just 1. Okay, so negative x squared plus 1, or write it as 1 minus x squared, will be a little cleaner as we move forward. So I now know the radius of all those infinite number of circles moving from left to right. And I'm going to plug that radius into our integral. I'll factor out the pi, keep my limits of integration from negative 1 to 1, and we're going the radius, 1 minus x squared, and we have to square that. Be careful. Some students put in just the r and forget to square it. So thinking of in terms of integration, my challenge is to integrate this. I maybe would think of using u sub. I have an inside function of 1 minus x squared. If your mind is working in front of me, if you can see in your mind's eye the derivative of that inside function, it will be clear to you the derivative of the inside function is negative 2x, and I can't offset that. So I've got to go to a plan B. How am I going to integrate this thing? Well, the truth is, if I'm going to go, I'm just going to go 1 minus x squared and expand that. I'm talking about 1 minus x squared times 1 minus x squared. And when I go 1 minus x squared times 1 minus x squared, the trinomial I get is 1 minus 2x squared plus x to the fourth. Now I feel real comfortable about being able to integrate the integrand. I got a power rule in reverse for all three terms. That constant 1 is just going to get, when I integrate the constant 1, I'm just going to get x. The other two are textbook, add 1 to the exponent, divide by the new exponent. So this step should make perfect sense to you. When I integrate 1, I get x. When I integrate 2x squared, I add 1 to the exponent and divide by the new exponent. That yields 2x cubed over 3. And the last term, when I integrate x to the fourth, I get x to the fifth over 5. It's now time to evaluate that integral answer from negative 1 to 1. So this is FTC1 in action. Don't forget about that pi in front. But as I look at what's going on here, there's the pi in front. This is what happens when I plug in the top limit of integration wherever I see an x. I'm talking about the number 1, and I get 1 minus 2/3 plus 1/5. FTC1 tells me you must subtract. Now plug in the bottom limit. Wherever I see an x, I'm plugging in -1. This is going to yield -1 plus 2/3 and then minus 1/5. So I have to make certain that I know how to work the exponents, etc., when I'm plugging a -1 in for x. So the nitty-gritty math here, 4th grade math, kick it out. You should get an answer here that's equal to, okay, so we've got a common denominator of 15 all the way across the board. And you can see I've got 6 terms up there, so I took the whole entire quantity inside the bracket, put it all over 15, did the math this way to get my final answer, 16 over 15 pi units cubed. This is a volume, so I got to make sure I'm in cubic units. The difference here, problem 1, we just went over the x-axis clean. Problem 2, we went over the horizontal line, y equals 1, which made things a little more difficult. In problem 3, example 3, we're going to rotate around not a horizontal line, but a vertical line. So stay tuned for that coming up. The third example of the disk method. Hope this is helpful. Stay tuned for example 3.